Afternoon. In the last lecture, we talked about several novel devices. There's the ultra-thin body. There's the double gate. FinFET was a special way of making a double gate device with the DT MOS. So the purpose is to show you examples how new ideas can overcome some of the potential limits to the scaling of devices. And these things would include things like we need very thin oxide to control the leakage current, right? Things like dopant fluctuation, shallow junction, the need for very high doping concentration to stop the leakage to get very small XD max. So any questions about that discussion? All right. So the emphasis I would like to say is not a specific novel devices that we talk about, but the concepts involved. What are the limiting phenomena? And there, I'm sure, will be even better ways to overcome those limiting factors. Okay? All right. What I want to do today, the first portion is to continue a little bit of that line of thoughts, and then we'll move on to a new topic, okay? All right. So let's look at this slides here. It's the International Technology Roadmap. We saw this actually briefly at the beginning of Tuesday's lecture. There was this idea that up to 0.1 micron solution being pursued, up to 0.35 micron, 0.035, 35 nanometer solution are not known. The roadmap doesn't go beyond that. But it appears, at least from the device point of view, 25 nanometer should be no problem. I even showed you a simulation that went even beyond 10 nanometer. All right, I think 10 nanometer gate lengths should be doable, actually. Now, in terms of year, what does that lead us if we take the 3-year per generation schedule that has been the historical trend, although the last few generations was introduced even faster than this. But the roadmap itself actually predicts or projects or shows this 3-year per generation rate into the future. So these numbers came from the roadmap. All right, suppose, let's say, every 3 years we need a new generation. Then you count from 35 nanometer to 25 nanometers, another 3 years. Then another 3 years we'll get to 18 nanometer. And this will take us to 2026 to the 10 nanometer. All right? Now, of course, in reality, there are other things that could cause a problem. But, you know, historically, there have been many other things that have given concern to whether the industry can continue this pace of progress. Things like product design. Now I'm giving you a little historical perspective now. Even today it's not so obvious. Certainly at some point it was not clear at all how the industry can design a chip with, say, more than 1 million transistors on it. If you put yourself in the shoes of someone who was designing transistor with only 1,000 transistor, already having a hard time doing it, certainly it's not so hard to understand. Of course, today the question is how going to design a circuit with 1 billion transistors on it. So often there's this question, product design would be the limit, but through ideas such as reuse, this IP model, and perhaps the building block of design will be, let's say, a processor itself will be a building block. And if you use that style to design, perhaps that's not going to be a problem. Manufacturing is always an issue, continues to be an issue. And in particular, lithography has always been the pacing item. And now it's even more difficult than ever because, you know, we're looking at 193 nanometer as the wavelength. Beyond that, it looks like the industry will be able to develop another lithography tool using 157 nanometer as the wavelength. The difficulty of using even shorter wavelengths light is because materials all become very absorbing. Just cannot find a transparent enough material to make lenses. Excuse me. Even for this, probably will be using crystalline calcium oxide, for example, to make lens. Example. So that's the difficulty. The need for reducing the wavelength is that because of the diffraction limit, as you know, for a while people have been saying, well, the line width limit will be equal to the wavelengths used. But as a result of the many clever ideas that engineers put in, now people say maybe we can make a line width that's half of the wavelength. All right, maybe. So 157 nanometer will be good to give us, let's say, 80 nanometer or 800 angstroms, right? And there's still a question, well, what's going to happen beyond that? This is not yet available, by the way, but perhaps by 2003, maybe industry will have this available. But beyond that, what's going to happen? Well, a very exciting thing that's happening is called extreme EV, extreme UV lithography, EUV, E for extreme. There's an interesting story. Well, what it is proposed to use a wavelength not 120 nanometer, not 100 nanometer, but 13 nanometer. It's a huge jump. All right. This is in the regime where people used to call X-ray lithographies, or soft X-ray. And unfortunately, soft X-ray had some lithography had some false starts. So over the years, it got a bad reputation. As a result, Professor Neurather of this department proposed at one time, some years ago, let's give it a new name. Let's call this extreme UV lithography rather than X-ray lithography. So that's what's known today. It's called EUV lithography. And, but what's interesting is that although it uses the radiation, which is classically classified as X-ray, but the way it's being done actually is very much like optics. You have a light source, you're going to collimate it, you're going to go through a mask and use other optics to focus it or reduce it to put it on a wafer for lithography purpose. So in that sense, it looks very much like today's optical lithography. The only thing is that we will be using reflective or reflection optics, not transmittive optics. In other words, not lenses, but mirrors. Mirrors rather than lenses. And what's special about this wavelength happens that at this wavelength, there's a particular multi-film coating that can give us decent reflectivity. Otherwise, you know, X-ray penetrate everything, right? How can you get them to be reflected? Well, it turns out there's a coating of moly silicon coating, and it will give you about 40% of reflectivity. 40% is not what we really like for high-quality lens, but it's marvelous. If you use 10 nanometer wave light, you don't get that. If you use 18 nanometer light, you don't get that. But it happens at 13 nanometer with the property of silicon and the moly, you are able to make lenses or mirrors out of it. You see what I'm saying? Okay. Same thing. What about a mask? You cannot do the mask the way we are doing now because any material will absorb these lights. Okay, the absorption is also an issue. So the mask also will be reflective. So what you do is you first put this reflective coating on a, let's say, a quartz substrate. In other words, just make a uniform piece of mirror, right? And then you etch patterns into this reflective film so that you get a pattern of reflection, of reflective pattern. You see what I'm saying? Okay? And you insert that into your optical path. All right? That's how you create the pattern. in this lithography system. So this is wonderful. In fact, just yesterday, there was a big press release celebrating a success of the first phase of this work, and Berkeley, actually, several professors play a key role. The work is done at Lawrence Livermore lab here with the Lawrence Berkeley lab, and UC Berkeley and Sandia labs, all done locally, and it's going to be very, very important if this indeed can be developed based on the diffraction considerations. Gee, 10 nanometer transistor, 10 nanometer technology will be okay, right? Okay. Or the beginning probably will only be used for the 50 nanometer node, probably. All right. Okay, so this just shows that all these barrier to growth engineers have been able to come with one surprising solution after another, and this EUV lithography certainly is a very surprising solution. Okay. All right. Power. That continues to be a problem. Certainly has been power for a long time, but I remember when this first became the forefront issue about 10 years ago. Again, Broderson and others at Berkeley took the lead to look at this, and some of you may know. And then very quickly people identified, in fact I remember a paper Professor Broderson gave this, he said there's a 1,000 time reduction in power possible just by starting from architecture, circuit design, technology. And so if you look at the, just to give you an example of how bad this power issue looked at. In the 80s, some professors have done research, not at Berkeley. The research is about how to remove a kilowatt from a chip, because that's a projection how much power dissipation will be on a silicon chip. Right? In retrospect, a little silly, but people have actually found ways to remove a kilowatt from one silicon chip. And the reliability, of course, is another thing. And we haven't said much about reliability. We talked about hot electron reliability, and later we'll talk about oxide reliability. But starting later today, we'll get into that topic. Device physics is basically the topic of this course, so we don't have to say very much. I think you already know everything. Fab cost. You may have heard people predict the fab cost is going to be the issue. You know, about 5 years ago, if you were sitting in any meetings where these industry heads talk, they always say, you know, every fab is costing more than $1 billion, right? That's going to stop this exponential growth of industry. Who's going to have the money to build these fabs? The funny thing is that today, the same group of people, if you get them together, you know, what they're going to say? They're going to say, you know, we're in a downturn of the industry, and the reason is overcapacity because there are too many of these $1 billion fabs under construction. So clearly, that price tag is preventing people from building these fabs. So as long as there is an opportunity for higher opportunity for return on the investment in this industry than in other industries, the investment will be there. And after all, the semiconductor industry is not a very large part of the world economy yet. Okay, later I'll show you what size is it. So we can afford to build $100 billion fabs. There will be no problem. As long as there's a return to that investment. So then there's a question of market saturation. To some extent, this probably eventually will be the thing. In other words, any exponential growth, if unchecked, will consume the entire world economy. Is that likely? Aren't we going to want to save some money to buy food and do other things? So eventually there's the questions, how much money is the world willing to spend buying semiconductor, right? So those are some of the questions we have to ask. So let's just look at this last question a little bit, okay? And what information we have on that. So if you look at the this plot, vertical axis is dollar amount, horizontal axis is years, okay? I plotted 3 curves here, and actually a student helped me took some data out of the library in the Haas School, so we made this plot. The top line is the gross world product, and this is a semi-log plot. As you can see, it has been growing exponentially people always amazed the semiconductor things grow exponentially. Everything grows exponentially. Look at this gross world product. Actually, it's better exponential curve than the other curves I'm going to show you. Has been growing at about 6% a year. And the second curve is the electronic sales, and that is sometimes called electronics factory sales of electronics. In other words, we're only talking about hardware. We're not talking about any services. So this will not include, Microsoft or not even MCIs, but this is really just a gear, maybe compact, the hardware that's made of electronics. That has been growing at about 11–12% a year. All right? And finally, on the bottom is the world semiconductor sales, and that's the actual semiconductor sales from factories that make semiconductors. And it has been growing at about 16% a year. Okay? And if you extrapolate these curves, just extrapolate the last curve, semiconductor and the gross world product, these two curves will intercept in 55 years. Okay. All right. So you would say that, gee, that means the entire world will be semiconductor. And this is what I was saying earlier. That's unlikely, right? And some other person commented, Professor Boker says, hey, maybe what's going to happen is that this last curve will push the top curve up. Maybe, maybe not, we don't know. Perhaps a more likely scenario will be at some point these curves will move more or less in parallel. That's kind of the steady state. That's about the amount of money the world's willing to spend on electronics, willing to spend on semiconductors, perhaps, right? But even though the growth rate of semiconductors is high, it right now actually is not a very large percentage of the world economy yet. It's only about less than 1%. Okay, so there's certainly some room to grow before you need to worry about the world runs out of money to buy semiconductors. So if we just look at these straight line extrapolations, if this past trends continue in the future, nothing changes. Let's see whether it can sustain the growth to 2025. We just reviewed the CMOS technology generation. Today is about 180 nanometer, 0.18 micron. At 2026, it's about 10 nanometer. Remember this first chart we saw this afternoon, right? Okay. Now the semiconductor sales as percent of the gross world product today is only 0.7%. At that point, it will be 5.6%. That's very significant. It's one of the largest industry in the world, but that doesn't seem to be out of the ordinary. It doesn't seem to be impossible. All right? At that point, I can tell you how large is the electronics industry. The electronic sales, I did not put the number down, but that's the middle curve of the three curve in the previous slide. Is that right? Okay. Instead of giving the number, let me introduce you another concept. Sometimes people give the word, say, semiconductor content of electronics. Semiconductor content of electronics. Okay? What that means is that on average, for every $100 you pay to buy electronics product, how much of that is in semiconductors? Do you see what I'm saying? All right? Yes? All right? Would you like to make a guess? What is it? What is that number? What's the semiconductor content of electronics? What do you think?
25.
That's actually very, very close, actually. All right? To get the number, of course, you just take the previous slide and divide this lower curve by the middle curve. Then you get the semiconductor content. Is that right? Okay? So if you do that today, actually it's less than 20%, maybe 17%, 18%. Sometimes people are surprised by how low it is. That's because we maybe tend to be thinking about, the more novel, really newfangled gadget. Perhaps if you want to buy the first of some gadgets, so it's going to be very expensive, and semiconductor is very expensive. But if you look at the overall electronic industry, semiconductor is only about 17%, 18%. Okay? At this point, turns out it's about 45%. doesn't seem to be impossible. Seems to be still reasonable. So, of course, I'm not making predictions. This is just projection, right? I just make those straight line projections. That's what we're talking about. Now, the last line, the world semiconductor sales in dollar amount, what is it? Last year is about $160 billion. This year, actually, I think it's more than that because it turns out it was stronger than that. But it doesn't matter. Let's not do that. If we just do straight line extrapolations, in 2026, it's going to be $8,000 billion. All right? Okay. Now, of course, part of that is due to inflation. So you can do something to take away the inflational part of the economy out of it, and you will still end up with $3,500 billion in the year 2000. Okay, now that's huge. So if you say at that point there's a real growth of say 5%, 5% of that, you see, it's already larger than the entire industry is today. So 1 year's growth can be more than the today's industry. Now, again, this is not a prediction, it's just projection. It could happen, and if it happens, certainly this industry has a lot of room to grow, and the only question then is, can we continue to have enough applications to absorb all the semiconductors? If you think about all the sci-fi movies, I certainly don't see much problem thinking that we're going to need all these high-tech stuff to make the world a lot more intelligent, right? All right, so that's that. If you have any questions, raise your hand, all right? So to end this discussion, I kind of like to sort of look at a little somewhat of a rhetorical, maybe it's not rhetorical, it's a real question. The question is beyond what I put down as title. The title is not as provocative as the real question is. Well, this slide is meant to address the question, what's the chance of some other devices coming along and knock the silicon, maybe CMOS, out of the way? Right? That's the question. I'm sure you have heard a lot about molecular device and protein and DNA computing. So what is the likelihood for that happening? If you look at the device, the desirable feature of the device is low voltage, large on current, small off current, small capacitance, high reliability, right? And also very important is compatibility with existing circuit architecture or new architecture. Now, what does that mean, compatibility with existing circuit architecture? Because what's compatible with today's circuit architecture will be things that have 2-3 terminals at least, should be complementary. In other words, a drop-in replacement for CMOS would be the best, right? Okay. And this is important because, if we give you free quantum device today, totally free, you can have 1 billion of it free. The fact is no one knows how to build something to do the job of a Pentium chip with it. That information is not there. That's a problem, right? And I'll give you another example. Historically, look at the way the solid-state device replaced the vacuum tubes. You know how that happened? People were making analog vacuum tubes out of semiconductor. That's how the semiconductor industry came up. That's how the transistor was invented. That's why we here still have the name, although we try not to use it on you, the triode region, right? And right, the triode region, the pentode region, the transistor characteristics. People were just making analog, making replacement of vacuum tubes, because vacuum tubes, we know that if you put signal on this electrode and current pass between those two electrodes, you get amplification. If you get amplification, you can get oscillation. If you get oscillation, you get communication industry. And we know these things can do that, right? And that's how these transistors were invented. Okay? So that's just example how important it is to fit into this existing the circuit architecture, right? And but if someone can truly invent something new to replace the infrastructure on the circuit system side, certainly fine. And the other thing is, it's very desirable to have compatibility with existing manufacturing technology infrastructure. That's another thing that's huge. You see, the same semiconductor infrastructure is used to make displays, for example, right? Right? MEMS in the future, right? Why there's a MEMS? Because they use the semiconductor manufacturing technology. And the gene chips, DNA chips, they're using outdated national semiconductor fab to make these chips. And so you can see this is a real asset. And it's going to be very expensive to replace that. So ideally, the new device will be able to use this existing manufacturing technology. So after you've thought all about that, it's reasonable to conclude it will be easier to improve CMOS than to replace it. Okay? Now, maybe at the end of this course, you expected this from me, but this certainly is not or was not conventional wisdom, maybe still not conventional wisdom. That is, many people feel, certainly, let's say 5 years ago, few people saw we could make CMOS to 0.25 or 25 nanometer, much less 10 nanometer. Instead, people felt it was very urgent to find some replacement for it. And I remember I was asked to give a paper at the nano electronics workshop, and I went there and told them that it should be nano CMOS transistors, nano electronics. But actually, that workshop just changed its name this year. So it's no longer going to be called nano electronics. It's going to be called the nano silicon devices workshop. It's so certainly the CMOS industry has a lot more room to grow, right? But it's very important, especially for those of us who wants to do research. There's always room for high-risk research and always room for surprises. There's always room for that. I asked my research advisor, John Whinery, maybe you don't know him, he's a marvelous person. He was a leading figure in the days of the vacuum tubes. And then he worked with, of course, some transistors and a lot with optics before he retired from Berkeley. So I asked him, were people surprised that when semiconductor replaced the vacuum tubes? He told me, not really. You know, they knew for decades that people were working on that, and they know things are getting close. And a lot of people were just moving in that direction when it really got close. In fact, after the transistor was invented, very quickly, all the companies just adopted to the new technology. It's in fact, the transistor was invented in 1948. By 1952, the conference ISCC, which was held in Philadelphia, already had 3,000 attendees, all right, which is not too much smaller than today's attendees. So this just means that, you know, people and industry are very adaptable. There's no need to be too concerned about what may be coming 20 years from now and not be ready for it. And so I think what needs to be done should be done, and in addition, there's always room for the really high-risk breakout research. Okay, but in terms of a concept business, other people would say, you know, if you really look at the successful breakthroughs, usually they don't come from trying to make higher performance or higher tech, but they came from lower cost. So, you know, I think there's a lot of truth to that. PC replacing mainframe, such an example, right? Instead of making bigger and faster mainframe, you do something that's cheaper but slower and smaller. And So, as you know, the newest professor in the department, Professor Subramaniam, is really looking at things that are very cheap, maybe things made by just jet ink printing. Just today in the elevator he told me they just made the first jet ink printing circuit, printed circuit. So those are the other possible directions, and chances are semiconductor has a role to play, but there could be maybe other materials involved. So that probably is more is another very interesting alternative to the scaling of the CMOS devices, right? So that there will be electronic devices in the fabrics of the clothing we wear, will be in the walls of every room, and those are certainly interesting ideas. All right, so that ends the discussion about I guess the future of semiconductor devices. Any questions? Yes, Jean.
Yeah, actually the international technology roadmap just for the manufacturing view, in 2026 we will have 10 nanometer device, but from the research point of view, that looks like the recent 5 years we could have some big improvement to that. So after 5 years, even 5 years later, so what kind of technologies will be in the research? Yeah, from the research point of view, could be the.
I think what Jane is asking is that, let's suppose in another 5 years, so a lot of people buying the idea that some double gate device can be made and can be made in up to 10 nanometer. Then what is there left for device research? I think that's really the question. Is that right? Yeah. That's a little bit like saying that once the transistor was invented in 1948, and there's nothing left to be done. You see what I'm trying to say? Maybe maybe it sounds like not the relevant answer. I think it really is, because just the fact that a transistor has been invented, a structure has been invented, right, doesn't mean that's the end. Now the question would be things like how you make this, what's the reliability, right? And all sort of things. Once you look at the details, there will be all sort of things we haven't thought about. That has always been the case, because you could have easily said this to me when I started the career in the 70s in looking at semiconductors. Certainly, transistors are well on the way, right? No one was looking for any breakthroughs. Do you see what I mean? You can easily have asked the question, what is there to do? Bipolar transistor is doing so well, MOS transistor is fine, so what is there to do? And certainly, and that would have been a reasonable question, right? Think about it. At that time, what is there to do? But just the fact that it's an important technology, you have to get to every aspect to perfect it because it's so important. That's the end of it. That's why there's so much job to be done. And what I try to point out by this economics projections to show you, not only you have same amount of work to do, in fact 10 times more, because in terms of importance, in terms of the funds that's available there to do this research, it's going to be 10 times more than there was in the past. Does that make sense to you? At that time, actually, there was even less money because there's less industry needed. There's less incentive to do it. Right? So what's amazing, really, is that as long as there is that economic significance, we'll never run out of things to do. Not only there will not be less things to do in the next 25 years compared to the past 25, there will be orders of magnitude more things to do. That's what it is. Okay. But that's certainly an understandable question. In fact, many schools, at some point, MIT's example, in the 70s decided they don't want to be in the silicon research, so they were out of it for more than a decade, and then came back in the 80s, right? And so certainly it's a matter of judgment. It's a matter of a view of the world, and But I definitely believe it's never going to run out of things to do. But this is what I mean by it's a very reasonable question. In the 70s, you can ask that same question also. It sounded just very reasonable. Exactly. All right? What is there left to do to be done? So the key really is there economic significance? Turns out that really is what it is. If there's economic significance, there's going to be that much work to be done. Okay? All right. Other questions. This is excellent questions. Difficult question. I don't mean to make it sound like it's easy. It's just that I'm opinionated because I've been thinking about it for many years. I've been debating with even our own colleagues for many years. But it's a very, very important question, very difficult one. Okay. All right. If no other questions, let's start with a new topic. Okay. All right. Okay. How did this come about? All right. Okay, what it is Chapter 7. This will be the final chapter that we will cover in the textbook. All right. By this time, you should have either, studied the other chapters. You either have studied because we covered them in lectures, or you studied them because they were assigned reading. Okay. Only chapter left. This is Chapter 7. So silicon dioxide, actually I should probably generalize it as a gate dielectric, okay? Although the textbook didn't talk about anything other than silicon dioxide, which is fine. I'll probably call it gate dielectric, right? And we'll start with silicon dielectric, silicon dioxide, silicon dielectric, gate dielectrics, okay? And we'll start with silicon dioxide. It remains the material used in gate dielectric. Okay. I kind of went through this argument with you, I guess, 2 lectures ago. This is maybe a little bit summary. You know, if you look in the literature, once in a while there will be a very thoughtful study that try to predict the minimum possible channel length, right? So-called scaling limit. If you look at the 70s, the paper will say it's about half a micron. In the 80s, maybe 0.2 micron. Today, everyone agree with 0.05 micron, right? And I think it's going to be 0.1 micron, less than 0.01 micron, right? But I think everyone will agree would be less than 0.05 micron. So then you ask yourself, gee, what went wrong? Why did these guys that are so smart couldn't see what can be done? I have to clarify that these studies are only looking at the physics of the device. They're not looking at lithography or anything like that, all right? It's not manufacturing, just from physics. There were predictions that that's what can be done, and now we see this, okay? And this is changing even in the last few years. It has been changing, right? So the question is, what went wrong, okay? Well, I already reviewed with you what is the proper way to carry out such a analysis. If you carry this analysis correctly, you always end up with the following conclusion, may not necessarily in these words. That is, gate to channel capacitance must be much larger than drain to channel capacitance, all right? So therefore, as you reduce the channel length, the gate oxide has to be thin. So really what determines this projection of the minimum channel length has to do with prediction of pin minimum oxide thickness. You see what I mean? If you believe we can only make 100 angstrom oxide, then you're going to conclude this is the limit, half a micron, that's it. You see that? Yes? Yeah? And you can probably see that in the 70s, it's not too surprising that whoever did the study would not dare to say that we will ever use gate oxide thinner than 100 angstrom. Right? It's not too difficult for you to visualize that, right? Maybe it is. That just shows my age. Now that's when they were using 1,000 angstrom as the gate oxide and still have problem with pinholes and with reliability, because that's already probably certainly probably just about thinnest film people use in mass production for any applications, right? So that's really what it is. It's because at that time people thought the thinnest oxide we use was 100 angstrom. And in the 80s, because we had more experienced oxide, then people say, oh, we probably can use 50 angstrom as the thinnest oxide. So the prediction is half smaller, right? And now people don't quite realize that, but really the only reason they have more confidence with scaling devices because now we are already using 20 angstrom of oxide, right? Another, and then we think we can even go to 10 angstrom of oxide, and then you will end up with this number. Do you see what I'm saying? Right. So the hard thing, turns out, is to predicting oxide reliability. Okay? So let's go to that topic. It's okay? All right. Once you know the oxide thickness, you can easily figure out how small channel you can scale and still turn it off, such as by doing device simulation. This study, for example, what I have in mind is a study by Hitachi, and they already had a very good simulator called Cadet, one of the first simulator used in industry for semiconductor device simulation. So certainly they know that with what oxide thickness they can, what channel lengths can be done. So what's the difficulty of predicting the future? Turns out is in predicting the scalability of gate dielectric. Right? So that's the introduction of why this is such an important problem, and also sort of give you an idea why it's so that it is difficult, because very thoughtful people couldn't figure out how thin oxide we could use. All right, so just said, usually people would answer the question by first saying, what's minimum VDD? Usually by thinking about noise, thinking about performance. They always end about 1 volt. Even in the 70s, people figure out it's about 1 volt is what you can use. And that's not too hard for you to imagine, I guess, that in the 70s, people already can see 1 volt is okay. And the problem is minimum thickness. We just keep scaling our prediction of how thin an oxide we can make, and that's where we're getting there. Okay, so this problem, first of all, is important for us to analyze, to appreciate, to predict what can be done in the future, and secondly, we should appreciate why it's so difficult to predict oxide capability or oxide reliability. All right, let's start with conduction in SiO2. We always say SiO2 is a good insulator. The reason it's a good insulator is that there are very few electrons in it. So if you take a piece of glass, put electrode on one end, put electrode on another end, you will see very little conduction because there are very few electrons. But if you take a thin film of glass, SiO2, between 2 electrodes, then you don't need the electrons in the conduction band of the oxide. Instead, current can tunnel through this barrier. Right? So for this reason, actually, there can be significant conduction through the silicon dioxide film. That's probably a better word, through, as opposed in. Right? And so the concept is, it's not a bulk conduction in the sense that a piece of silicon will have a conductivity. The term conductivity is almost meaningless in SiO2. Right? But when you have a thin film, then current can tunnel through it. In that sense, that the silicon dioxide can conduct current. Is that right? Okay? All right. And what do we mean by tunneling? So when we apply a voltage between the 2 terminals, we don't even care which is substrate, which is the gate, so we just call it cathode and anode, right? The side that has a higher voltage is called anode, and there the image diagram is pulled down, right? So now electron from cathode can tunnel through this barrier first into the conduction band of the SiO2. Once electrons are in the conduction band, actually they can drift very easily through the oxide. The electron mobility in SiO2 is difficult to measure because there's so few electrons, but usual estimate is actually it's probably 20 centimeters square per volt per second or something like that, which is a very good number if you think about it. All right, it's not bad at all. So any electron in this thin film easily flows through the SiO2 and get collected by the anode. Is that right? Okay, I'll show you some other picture for this a little later on. And this conduction mechanism is called Fowler-Nordheim tunneling, because Fowler and Nordheim first worked out the following theory. And they worked out through the using WKS approximation, solving the tunneling probability. They figure out the current density is equal to some constant oxide field squared. Exponential minus a constant over EOX. All right? Okay? So EOX appears twice. Turns out the pre-exponential term is not so important because, you know, the exponential term really dominates the dependence on the oxide field, right? And the exponential term has the form of minus constant over EOX. And this is similar to the field dependence of the impact ionization coefficient. I'm not trying to imply that there's some link between those two mechanisms. There isn't, all right? But what I'm trying to point out is that actually this type of field dependence is very common in semiconductor physics. In fact, they all seem to have to do with this, all right? And from the kind of interpretation we talk about in the hot electron effect, you may remember it has to do with the energy argument, right? If you have electric field, electron have to gain certain energy, then it's going to follow this relationship. So from that angle, maybe it's not too surprising to you that we see this. Actually, I shouldn't say that. This did not even come from energy, and just come from the tunneling probability. Also give you this. All right. Energy consideration, you also have this kind of relationships. For this reason, that you see this exponential minus constant over E relationship a lot. Okay. So tunneling also has a relationship. All right. So if you really want to simplify this equation, you can even ignore this EOX squared term. It just says it's a constant exponential minus B over EOX. Okay? All right. And these constants B and K are determined by things like, well, in fact, I'll give them here. B is equal to, this is the Fowler-Nordheim equation. This is what they derived. B is equal to 8 pi square root of 2 mass of the electron effective mass in the oxide, or while they tunnel through the oxide. Phi b, 3½ power. Phi b is this barrier height. The 3.2 eV is what we call phi b, all right? The barrier height, the barrier that you are trying to tunnel through is called phi b. And then K is equal to Q cube Mn 8 pi MOX phi b, okay? This Mn is electron effective mass in the silicon where they're still in the cathode. All right? Okay. So when you put this number in, we have actually constants here. But usually we don't care too much about the constants in the K side. We just fit with some data. For the B, because it's it's the current behavior will be very strong function of B. So this is rather useful to keep in mind what it is. And if you put number in there, you find about 270 megavolt per centimeter for SiO2, roughly. Okay? All right. So if you now make a plot of this log J against V, this is the equation you see. Okay? If you plot log J versus V or E, doesn't matter, V or E, you won't see a straight line. Instead, you see a line that kind of bends concave downward. And this is the same thing we see in the substrate current behavior. This has to do with this relationship, exponential minus B over E, right? It's not exponential dE, right? It's exponential B over E, so it will not be a straight line, okay? So just get familiar with the shape of the curve. And if you have more oxide thicknesses, of course, you need larger electric voltages, right? If you replot this against the E, oxide thickness, voltage divided by thickness of the oxide, you end up with one curve. You see what I'm saying? It's only a function of electric field and not a function of a voltage and thickness separately. All right? Okay. So that's known as Fowler-Nordheim tunneling. Now I'm going to change gear and tell you about another tunneling model. This is a picture of Fowler-Nordheim tunneling, all right? It's okay? All right? Yes? Under this condition, how many volts is applied across this thin oxide? How would you estimate? What can you use as a reference in order to answer my question? First of all, we should identify in this diagram what is the oxide voltage. What's the voltage drop of the oxide? What we have been calling Vox. Remember, there's the phi B band-bending oxide drop, and then there's the Vox. You add them all together, and VFB, you get VG, right? So what is Vox in this diagram? Do you agree? This is Vox. It's the difference between this point and that point is Vox. Do you remember? Do you agree? And now I'm asking you, how many volt is the Vox in this diagram that I put down here, roughly speaking, if this is a silicon and silicon dioxide system? Is there a reference in this diagram that give you some number in terms of EV? You said there is. What is it?
I think that's a barrier height.
Very good. Barrier height is this quantity, right? And how large is barrier height?
3.2.
3.2 EV. So this is 3 EV. Given that, how many volt do you think is applied to the Vox in this example? How many? Okay, so, somewhat larger than 3.2 volts, right? I say 4 volt. Okay. In other words, if you apply more than 3.2 volts, then you will end up with this picture. But 3.2 volts is already a fairly large voltage today. What if you apply smaller voltage than that? The picture will change qualitatively into this. Is that right? The tunneling will no longer be under a triangular barrier. It will be under a trapezoidal barrier. Do you follow what I'm saying? Okay. And indeed, this actually happens at a point even larger than VG equal to 4 volt of 3.2 volt. It's about where VG is equal to 4 volt is where this cross, because there's also work function difference. So when you 4 volt on between the substrate and the gate, you are pretty much at a transition between these. Okay. Again, that's another way to say today we should be more concerned about this new situation. This has a name called direct tunneling. All right. Direct tunneling simply means you go from a conduction band on one side, of silicon, to the conduction band of silicon on the other side of oxide. You don't go through the conduction band of the silicon dioxide. Do you see what I'm saying? All right. So that's called direct tunneling. Is it okay? All right. Now, because the shape of the barrier changed, you probably would expect the Fowler-Nordheim equation would not apply anymore, right? That you need some other kind of model. And indeed, it's true. It no longer applies. And actually, a student from Berkeley, Klaus Schulgraf, was the first to derive this equation for this direct tunneling case. And this is the way it looks like. Okay? So it's exponential minus B over EOX 1 minus VOX over phi B 3/2 power. Okay? All right. Now, what's special about this, other than it looks more complicated than the other the equation? Turns out, qualitatively, there's some big difference. First of all, if you just like this J over V relationship, you're going to find that in the Fowler-Nordheim regime, current drops very rapidly with V, a strong function of V, whereas once you enter direct tunneling regime, they're not strong function of V anymore. Okay? Later, I think I'll have some actual data to show you. It's depressingly insensitive. We say depressingly because, we hope they're very sensitive, such that by going from 2 volt to 1 volt, leakage current drop by orders of magnitude. Then we don't have a problem with leakage, right? But they don't. All right? So that's the equation predicts that they don't. Okay? Secondly, they are depressingly sensitive to oxide thickness. By changing the oxide thickness by 1.2 angstroms, we end up with 10 times more current. All right? So roughly speaking, every 1.5 angstroms reduction in thickness gives 1 order of magnitude of current, more current. Okay? More sensitive to the oxide thickness in the direct tunneling regime than in Fowler-Nordheim regime. Okay? Yes? And finally, maybe you already gathered from those 2 separate statements, but actually it's not so obvious, that if you did replot this against EOX, you will not get one single curve for different oxide thicknesses. On the Fowler-Nordheim side, you get one single curve, no matter what oxide thickness is. But in directed tunneling side, there's things like that. Of course, there's still function of E fields. I didn't mean to say it's not function. It's like that. And this is increasing oxidants, or let's say reducing T-ox, all right? This is as the T-ox gets reduced. This is what you'll see. In other words, J, the current density now is not a function of oxide field only. That actually is probably the most succinct way to describe the problem we're facing today, although that's not a standard way people describe it. In other words, we have been scaling the oxide very much throughout the last few decades. So what we're doing today is not new. What is new is that it used to be, as long as we keep the field constant in the oxide, we don't get more leakage. All right? Okay? Now we enter into a regime, even if we keep the field constant in oxide, even if we scale the oxide thickness, even if we scale the power supply voltage together with oxide thickness, which we are doing, by the way, we still end up more and more current, leakage current. You see that? Yes? If we're in the Caldwell regime, we'll not have that problem. No matter what thickness of oxide, as long as we keep the field constant, we'll get the same current. All right? But we're not. That's why we're in deep trouble right now. Okay? Yes?
Why is there a sharp cutoff between the two tunneling regions? I mean, you'd think that both tunneling or the direct tunneling could happen in the Fowler-Nordheim regime?
Sure. Maybe I mislead you by saying it's a sharp transition. You know, this is a free hand. Whether it's sharp or not, it's hard to say. But if you really look at the actual data and actual plot, it's about this sharp. Is this sharp or is this not sharp? Oh no, it's about this. Okay, there's transition. There's nothing. It's not saying one suddenly stop. But the fact is, you know, just because they two have such different slopes, I guess that must be the reason why you put the two together. It's still pretty sharp. Okay. All right. So that's a discussion of the conduction. So now you all know a lot of electrons can pass through the oxide. So oxide is really not that good insulator. Next, what happens when electron pass through the insulator? Okay, goes through SiO2. Several things can happen. One is electron can get trapped. All right, if they get trapped, then VT will drift. All right. Now this particular problem is more serious when the oxide is thicker and less serious when the oxide is thin, other than the fact that we're passing through, you know, orders of magnitude more electrons, okay? Certainly you can imagine if the oxide is thick, there's more chance for electrons to get trapped, right? There are simply more traps in that, right? Is that right? So with thinner oxide, fortunately, even though we're passing through thousands and millions times more electrons now than in the case of a thicker oxide, we actually don't see more VT drift, very fortunately. Okay? Just because there are fewer traps, and maybe when oxide is thin enough, once they are trapped, maybe they can be detrapped again. So this is not a serious problem, but historically this is a more serious problem. Okay? In fact, we just recently mentioned reviewing the hot electron behavior of PMOS as dominated by electron trapping. Do you remember that? Electron trapping. Yes? Is that right? Yes? Okay. And I also said in more aggressive technologies, electron trapping seems to become now equally important, or another mechanism have become equally important, and that's interface trap generation for PMOS, right? Used to be dominated by electron trapping. Yeah? So now that you have heard what I said about this, you could certainly very reasonably suspect, hey, maybe part of it is because electron trapping is actually less efficient in the thinner oxide. And I do believe it's true. But I think actually even more important explanation is that interface trap generation has become more efficient in the more aggressive p-channel transistors. All right? So this still is a concern, but it's not expected to be more important as we continue scaling. Next, holes are created. Now we don't know how holes are created. Even today there's still some debate. For a long time, for example, the impionization is a favored model that is somehow as electron pass through the SiO2, it got so much energy it actually caused impionization in the oxide. Of course, that's the day. Those are the days when we were studying hundreds angstrom thick of oxide. We put 20 angstrom, 20 volt across the oxide in order to create tunneling and all that. And so in that case, it's not difficult to think the impionization happens. But today, it's only a couple of volts across this oxide, and the band gap of SiO2 is 9 eV. It's very difficult to think that we have impionization, right? So that's why a few years ago, again, Klaus Schulgraf, the research here, we really endorsed this concept of anode hot hole injection. It's not our original idea. Even in the 70s, people already know one option is called anode hot hole injections. But we propose that truly is what's responsible for reliability, for breakdown, and work out the breakdown theory based on that we call anode hot hole injection theory for SiO2 reliability that I'll review with you. If we don't finish today, we will not. We'll continue through next lecture. But in that model, the concept is that electron tunnels through this to the anode. When it arrives to the anode, it has a lot of energy, right? All this much energy is going to be given out. Are you following what I'm saying? All right. Yes? Now, this energy can be used to create a hole that's deep in the conduction valence band, all right? Maybe these two arrows should be drawn with equal lengths. We didn't quite do this quite right. Why don't I make this, I don't know how to correct this. Maybe move this up a little bit, all right? Maybe move this hole up a little bit, right? The idea is that we can create a hole that's deep in the valence band. Then this hole will tunnel through, right? Yeah? Because this barrier height is not so large, right? It's not like a cold hole, so it can tunnel through, and that's how hole can be created. Is that right? Is that correct? All right. Now, I'll explain later why hole is so important, because there are many independent evidence that is this holes that eventually leads to interface trap generation and breakdown. I think I already mentioned this to you, the statement to you before more than once. That is, it's believed that the hole injection is a precursor to the creation of interface traps. All right. So for now, let's just bear with me and assume that hole injection is important. So I want to say a little bit more how to detect this hole injection. It's a clever method. It's called a charge separation technique. Okay. How can we characterize, how can we measure and detect that holes are inject created when we subject the MOS capacitors through this tunneling, right? We can easily measure the tunneling current, just a gate current. But how can you measure this current, this hole being created, right? Okay. What you do is this. You take an N-channel transistor, P-type substrate, source and drain. See that? You connect the source and drain together and ground it. Source and drain are grounded, okay? Similarly, the substrate is grounded. You can have a ammeter, of course, before you hook it to the ground, right? So substrate, source, drain are all grounded, right? Yes? You do put an ammeter in the substrate. Now, we now apply a bias between the gate and the source and drain, and the substrate, because all three are grounded. Source, drain, and substrate grounded. We now apply a bias between that ground and the gate. Is that right? You see that? It's very simple, right? The simplest way to stress this transistor is just like that. Is that right? You ground source and drain and the substrate, and then you apply voltage between the gate and the ground. Okay? You also can put an ammeter there to measure the gate current, right? So I guess we should put this here, right? This is what we mean. We want to put the ammeter here. Right? That's not it. I'll put the ammeter there. Is that okay? All right. Put the ammeter there. Okay? You got the... now, you just, for example, ramp up this VG. Okay? So as you ramp the VG, what do you think you're going to see in this IG? what this top emitter measures what's called gate current. Is that right? Yeah? What shape do you think IG would look like versus VG? Do you know any equation or any model for this IG as function of VG? Anyone knows a model for that? Does Fowler-Nordheim tunneling sounds familiar? And that's what you expect, right? That's all. You're just applying a voltage between, or maybe I made it too easy. I should clarify this a little bit. Particularly, we're applying positive voltage, right? If you apply a positive voltage, then the surface is inverted. Is it correct? Is that right? Yes? Surface inverted, yeah? So you can consider this as just a very thin n plus layer if you wish. So you have now n layer, you know, from source all the way throughout the channel to the drain, right? And this n layer is also grounded at the ground potential. Is that right? So what you're really looking at is the Fowler-Nordheim tunneling between the gate and this inversion layer. That's really what it is. Okay? All right? So what you expect IG to look like is a Fowler-Nordheim curve. And that's fine, all right, if you plot log IG. Okay? Now, well, this log IG is exactly this top arrow, is electron tunneling, right? And by the way, it's tunneling from where to where? From substrate to the gate or gate to the substrate? Which side is the injector? Which side is the anode? The electron always tunnel from the negative side toward the positive side, right? So it's tunneling from the inversion layer into the gate. Is that right? So this is the gate. Okay, this is also the anode. That's what we call this anode hot hole injection. Okay, so inversion layer electron tunnels through the oxide into the gate, right? Give up that energy. That energy creates a hot hole tunnel into the oxide, drift to the substrate, right? So what will hole do once it gets into the substrate? What does it see? It sees a drift electric field pushing the holes into the substrate, right? Because this is a inversion, so the field is to pull electrons to the surface, form inversion layer. The same field will pull any hole away from surface into the substrate. Is that right? So that hole will flow out of the substrate as a current, just like I sub, right? And except that this time it's not created by impionization, but created by this unknown mechanism, right? We believe it's due to this anode hot hole injection, but used to be thought as impionization in the oxide example. It's okay? All right. So that's how we can characterize that. And if we characterize that, we can find it can also be modeled as hole current is proportional to IG exponential minus AT over EOX. IG makes sense because IG is the origin, is the cold hole, is the holes going into the anode, right? Right? So you can interpret the exponential term is really just the efficiency of hole generation. Is that right? It's really efficiency of hole generation is hole current divided by the gate current, which happens to have, again, the same kind of functional form, exponential minus a constant over EOX. And the constant has been measured to be about 80, okay? Are you following? Yes.
But it looks to me that the PN junction is also forward biased.
No, it's not. Let's see why you feel it's forward biased. This body is ground, right? And this M junction is also ground. This is also ground. So therefore, they are not forward biased.
But is there an electric field that try to push a hole, you know?
The electric field that we're talking about is this. If you draw a energy band diagram along the dotted line that we're talking about, right? And remember, surface is inverted. How does that energy band diagram look like? Do you agree that it looks like this? It's this field that I'm talking about that will push any holes that come into the substrate. All right? So let me use this picture to draw what we're talking about. Electron tunnel from the inversion layer into the anode. Okay? All right? And I should have be more careful doing this, but it's fine. So electron coming into the anode, right? It gives up this energy, create holes here, all right? and the hose tunnels through and gets pushed into the substrate. All right, and then we can measure with, pick it up with ammeter. Okay. All right, neat technique to study this phenomena. Do you have questions, Riren? Please.
How do you know it's hole injection
and not impregnation in oxide, for example?
So it's the electron current which causes this hole injection.
Yes.
I'm just trying to see how you can pinpoint the physical mechanism involved.
Nobody can. That's still, in fact, still a small percentage of the researchers still not convinced it's a hot hole, annual hot hole injection, and but I think most people agree this is the correct interpretation. Some people think what it is this electron energy actually breaks a hydrogen silicon bond. It's the hydrogen actually drifts across the oxide, and that's what we're measuring. All right, so it's difficult to determine, but most people feel this is the best explanation. Okay, right, and certainly I have many other ways to show. One is the time response. This thing is basically instantaneous. If you apply a pulse, you will see this coming through right away. It's a little hard for me to see. We can break bond, hydrogen can diffuse there within milliseconds or less, but I'm not expert on hydrogen diffusion, so maybe you can. But this basically is instantaneous. As short pulse we use, we can see this. All right. So, but it's through this kind of study to try to determine the mechanism. To answer your question, how do you do that? You just try to think about, if it's that mechanism, then you should have that property. Let's go look for it. If it is the mechanism, then you have that property. Let's go look for it. So usually research is done that way. Okay? All right. Okay. So once we have holes, what can happen? And why is hole so bad? Why is hole trapping? Hole trapping is more efficient than electron trapping, because hole has very low mobility in the oxide, and in fact it's tremendous discrepancy of how mobile holes are in the oxide. But general assumptions that the hole can be trapped more easily, a lot more easily than electrons. All right, so hole can be trapped. As a result, VT drop can be either positive or negative. If electrons are trapped, then we get positive shift in VT. That is, you need a higher voltage to turn on N-channel transistor. Similarly, if holes are trapped, you get the opposite side. So when you measure the oxide threshold voltage, sometimes you see voltage increasing with time, sometimes you see decrease with time. And it's very easy then. Anytime you see voltage increase with time, you say, oh, electron trapping. You see decrease with time, you see hole trapping. All right, that's easy. But there's a third thing, that's the trap generation. It's believed that hole trapping will eventually lead to the interface trap generation. Again, the correlation is fairly easy to establish. You know, you have trap a hole, and then after a while you get interface traps created. But what's the actual mechanism? It's difficult. Just like Sriram asked earlier, if you had a theory as to how this happens, how do you prove it? It's difficult. But many evidence point down to actually holes actually trap the holes recombine with an electron in the oxide, and that energy is given out to break a bond to create interface trap generation. Those interface traps are very troublesome. Okay, earlier we were saying that delta VT is becoming not as important because even if you have electrons or holes trapped in the oxide, even if you have them trapped there, as oxide gets thinner, do you know that delta VT becomes smaller? Because delta VT is equal to the charge trapped divided by what? Do you remember? Cox, remember? Right? Yeah? Remember? The effect of trapped charge on the delta VT would be charge divided by Cox, right? I always said there's a minus term in front, remember that? Okay, that's what I'm talking about here. Okay? And so even if you have the same number of trapped charge, just because the arc is getting smaller, arc is getting smaller, smaller, the delta VT is getting smaller, smaller. All right. So the general observation is that this drifting in the threshold voltage is not so much important. And even the same amount of NIT will give us smaller, smaller delta VT. But the impact of NIT on for example, the mobility, that's not going to be any less, whether the oxide is 100 angstrom or 10 angstrom, right? If you have a certain amount of charge at the interface, they're going to have the same effect on the mobility, right? Doesn't matter oxide is thin or thick, right? You see what I mean? So in the future, I think the impact of trap generation on the mobility will be the main problem, and not so much in terms of the drip of the threshold voltage. Right? Another problem these things creates, that they create quote-unquote oxide defect, oxide damage. Again, it's not so clear what oxide damage is, but more and more people are beginning to be willing to think that this oxide damage really is just electron traps. In other words, not only creates interface traps, also creates electron traps throughout the oxide. Let me just use a square box to represent electron traps, as sometimes done. Okay? Why is electron traps a problem? Because once you have electron traps, tunneling current is enhanced quite dramatically, because electron tunneling can go through the stepping stones, right? You tunnel into a trap, to another trap, to this, and you can imagine this can increase the tunneling current by orders of magnitude. Is that right? Because otherwise tunneling through this barrier is still not so easy, but now you really made it easy. So this is known as stress-induced leakage current. So that's the first thing to do, to see, all right? And then maybe it's believed this somehow is related to breakdown, so this really should be next entry here, okay? And so we're going to spend a lot more time talking about breakdown. But first, let's look at stress-induced leakage current. Do you appreciate why that can cause stress-induced leakage current? Is that right? Okay. That means after stress, the gate tunneling current becomes much larger. All right? That alone can already be a reliability issue. It turns out it is for non-volatile memories. It's not for logic devices, but it is an issue for non-volatile memories. Very important. Okay? And so stress-induced leakage is a result of this damage of oxide, and damage perhaps nothing but electron trap generation. And finally, it's known that if you just keep stressing even more, at some point, this current suddenly jump to by orders of magnitude. That's what we call breakdown, of course, right? Now, what is breakdown? What causes breakdown? Again, it's controversial. It's not so obvious. But generally, it's believed to be this, all right? Suppose you have, let me use a fairly thick oxide as example, okay? Original tunneling current is very small. You have one trap here in a tunneling current already increased by a tremendous amount, all right? Right? But it's just one trap, so therefore, in terms of the total magnitude of current, maybe each trap, in fact, we think we know, each trap probably conducts about, I think, I forgot, so don't quote me on this, I believe it's only about 1 nanoampere or something like that. But as time goes on, there will be more traps formed. Is that right? Therefore, if each conducts 1 nanoamp, as time goes on, will be 2 nanoamp, 3 nanoamp, 4 nanoamp. So this is why things is changing with time. Is that right? But if at some point this happens, that there are 2 or 3 traps that happen to line up. Now, probabilistically, it's highly unlikely. If you look at the top view of this transistor, there's so much area. It's very easy to see why there will be one trap here, and the next trap will be somewhere next, one next, right? Now, why should they just happen to line up? That's unlikely, right? But if you wait long enough, it's going to happen. Could happen. And when it happens, now the current becomes, it's not just add another 2 nanoampere to it. This thing suddenly becomes microamp. Right? Maybe actually we think it's 100 microamp. And at that point, and because it happens at such a low area, it's actually believed there will be a significant amount of heating. And in fact, there's evidence the silicon even melts, right? So this can lead to a really severe runaway and eventually breaks. This is what we call breakdown. So when things break down, if you do failure analysis, you actually very often can see very large problem there. Oxide is often a hole. Okay, this we think is because of heating. So what actually heating part, all that probably only takes less than 1 nanosecond, maybe 1 microsecond. What determines whether oxide will break down in 10 years or break down 3 months after you sell it to your customer is how long it takes for this trap to build up. Is that right? So that's known as the lifetime of the oxide. It's not how long it's going to generate heat to melt something, but rather how long it takes the trap to build up. So if you want to understand reliability, try to predict how long the circuit will last, you have to have some way of predicting how rapidly these traps are created and what time the oxide will break down. Okay, any question about this picture of breakdown? So it's like the oxide always goes through a life cycle. At the beginning, it's kind of pristine, clean. Actually, may already have a few of these traps, but very few. And then as you stress it, because of whole generation, then oxide trap generation, you start to see leakage current gradually building up with time in a very smooth way, until at some point it just suddenly breaks down. Okay, second breakdown we think is because a string of traps probably gets generated. All right. Once the string is almost complete, in fact we think maybe it's not breakdown, but the current is so large, then the chance of generating more traps along this path is also enhanced. Because remember, the damage itself is a result of passage of electrons, right? So there's this positive feedback. It's okay? All right? Then there's always a question, why would the breakdown happen at this particular spot, not another spot? Well, we can talk about that later, but conceptually you probably can agree. Probably some paths is weaker than others. In other words, the oxide is not totally uniform, right? And so how can you describe that weakness? People use the word defects. That's a very good word. The only problem is that it means different things to different people. And in fact, this picture has been changing in the minds of people who do research. Let's say 20 years ago, when you see oxide defects causing breakdown, everyone will assume it's a big piece of dirt, right? And that's why it breaks down. And today, we actually don't think it's that. It could be maybe just single metal atom, or maybe just because two bonds happen to be weaker and they happen to lie together, and that's already enough to be to make that point the latent spot that will eventually break down. All right. So the word, what defect causes breakdown is also changing. Okay. So we really haven't get into the mathematics yet. So next time when we meet, we'll give you some equations and work out the theory for the oxide reliability. And then I think we're going to have an hour talking about the high K dielectric, new technologies, where things are going. All right? Okay. I'll see you on Tuesday.